You're in the right room. This is the right title slide. A Tale of Two Kittens. I want to share a story that gave me a lot of inspiration during my own PhD time. In 1963, two scientists, Held and Hine, they did an ingenious experiment. So what they did is they put two newborn kittens in this device that looks like a merry-go-round. And these two kittens have not yet seen the visual world, and it's just kind of their first moments in the world. So what happens is the active kitten on the right-hand side, it can move freely, while the passive kitten is constrained to this basket, while the motion is transmitted over this little hinge between the active and the passive kitten. And the difference is the active kitten can move around freely and observe the world, while the passive kitten can also see the world, but it does not control the body. It cannot control its own motion. And after a few days, the scientists test the kitten's visual system, and they found that only the active kitten developed a healthy visual motor loop, and the passive kitten was not able to respond to things like visual cliff or avoiding obstacles. And note that both kittens experience the exact same visual sequences, right? The data is same and mirrored, but the only difference is the agency that the kittens took. And these days, we have a very powerful passive kitten, and its name is ChatGPT. But for us humans, when human babies were born, we don't go to Wikipedia and read terabytes of text from the internet. We play with objects, we touch them, taste them, break them. We experiment, we fail, we try something new again. So people call babies scientists in the crib. And embodiment and active agency are what make us human. So I believe the future belongs to embodied AI here. And today, let's talk about NVIDIA's big plan on building embodied AGI, Project GR00T. And my name is Jim Fan. I am leading the GEAR group, which stands for Generalist Embodied Agent Research. So in March this year, this is a scene from GTC, NVIDIA's biggest annual conference. And here on stage, we have 10 humanoids. 9 of them are electric or mechanical, and there's one biological humanoid in the middle, and his name is Jensen. So this is the announcement of Project GR00T, which is NVIDIA's goal to build the AI brain for humanoid robots. So you have a very natural question, right? Like, why are we doing humanoid? Well, because we know it works, right? The human form factor that you and I all embody right now is what produces all the economically valuable physical labor. And the second reason is we're entering an age where humans and robots, they need to work hand in hand. And for humanoid robot form factor, it's much more socially acceptable. It's much easier for humans to work alongside robots to predict what a humanoid would do compared to some spider robot that is super unpredictable. And the third reason is a bit more pragmatic, right? Because the world that we live in are designed for the human form factor. All the public facilities like hospitals, restaurants, supermarkets, all the tools and equipments that we have are designed for 2 hands, 2 legs, and 5 fingers for each hand. So it's just easier for the humanoid to use all the tools and blend in the world that we already built. And the second question is, why are we doing this now? Actually, towards the end of 2023, beginning of this year, we have seen a surge in state-of-the-art hardware for humanoid robots. And just to name a few, and this is by no means exhaustive, there's Tesla Optimus, Boston Dynamics E-Atlas, where this robot kind of does some crazy, moves like 360-degree joints. That's kind of breaking your brain, and then Figure F02. And also we see this trend of the price of the humanoid and the cost trending towards a very low value. Actually, humanoids have been around for a while, right? In 2001, NASA has built something called the Robonaut that costs north of $1.5 million to build. And just a couple of months ago, Unitree announced G1 that costs about $30K, which is the price of a regular car that most of the households will be able to afford. And it just so happens that there's a general pattern where the manufacturing cost of a mature product will tend to the cost of its raw materials. And a humanoid robot only takes 4% of the raw material that's needed for a car. So it's possible that this exponential decrease in cost will go even further. And that makes now a good time, right, to enter this space. So Project Groot, that is NVIDIA's moonshot at building the AI brain for humanoid robots. And I cannot take all of you to our lab, which is about 50 minutes drive away in Santa Clara headquarters, but let me take you on a virtual tour. This is in our lab in Endeavor Building headquarters during March GTC, where we had 4 different types of humanoid robots from partner companies. So know that NVIDIA doesn't build our own robots. We rely on the hardware from our partners to develop our AI on. So during GTC time, we had 4 different types of humanoid in this lab. And at that time, it was the most number of diverse humanoid species per square feet anywhere on Earth. And if you wonder, where does the name Project Groot come from? It actually stands for Generalist Robot 00 Technology. So we're putting zeros here because it looks like Star Wars, right? It's a serial code for the robot. And the keyword here is generalist. And that is the strategy that we're taking, right? So there is one successful field of AI, and that is the field of NLP. Before 2019, NLP has been around for a long time. And there are a lot of specialist systems like sentiment analysis, recommendation system, summarization, information retrieval. And all of these will require different training pipelines, data pipelines, evaluation, and so on. It's a very complicated field. And then in 2021, ChatGPT came and just blew everything out of the waters. It is one generalist robot, generalist model that you can prompt and tell it the task that you need to do. And then once you have this generalist moment, you can specialize it back by prompting it, fine-tuning it, distilling it down to smaller models that once again are domain experts. And we call that the specialized generalist. And it's almost always the case in the historical trend that the specialized generalists are way stronger and much easier to maintain than the original specialists. And that is the success story from NLP. And for robotics, we're kind of still stuck here as we speak. Most of the robot systems these days are specialists. They require special hardware and special algorithms that may or may not even be learning algorithms, may or may not involve machine learning, specialized data pipeline for every use case. So what we do, we copy homework, right? We copy homework from the field of NLP. And we hope that Project Groot will be the generalist moment, the foundation model moment for robotics. And then after that moment, we'll specialize it back by prompting it, distilling it, fine-tuning it back to the special use cases. And we hope that the specialized generalist robot will be much stronger than all the robot systems that we have today. So this is a guiding principle that we operate on. But how do we really make this a reality? So today I'm going to talk about some blueprints. 3 principles. If you take home anything from today's talk, just 3 things. The data pyramid principle, the matrix principle, and the foundation agent principle. And all of my daily work, our team's research adhere to these principles that I'm sharing today. The first is data pyramid. Have you wondered why robotics is so hard? Why is NLP solved first, but we still don't have generalist robot? Well, there's one thing called the Moravec's paradox. which says that things that are easy for humans are actually really hard for machines and vice versa. But have you thought about why? And I would say the culprit is on the data side, because you can download terabytes of high quality text from the internet. You cannot download motor control signals from the internet. I wish, but it does not exist. So for robotics, we need to build our own data set. And what does the data pipeline look like? It's much more complicated than just training text foundation models. So let's work our way downwards from the top. And the top is obvious, real robot data, right? You just collect some human demonstrations on the real robot hardware. And unfortunately, you are limited by a fundamental physical limit of 24 hours per robot per day. But still, this data is super useful. It's a gold mine because it's directly aligned to the real robot hardware. So how are we collecting that? How do we make data collection as intuitive and easy as possible? Earlier this year, Apple announced Apple Vision Pro. And then we have these really kind of cyberpunk moments. You know, this is on New York subway and someone just kind of typing randomly in the air, super weird. But these days, this is a norm. So we see Apple Vision Pro using this way, and we thought, how about we apply this to robotics? So we built a system where a user wears Apple Vision Pro, and you can teleoperate both a robot in simulation and also in the physical world. Simulation here, and this is a physical robot hand from a humanoid. And the idea is very simple. Vision Pro is tracking your pose, your hand pose, and then retargeting it in real time to the real robot. And additionally, you can also operate a robot in simulation. And in this way, you can teleoperate anywhere. So this is what NVIDIA built, the Omniverse Cloud. And on this cloud, you can connect any XR device and then teleoperate a virtual robot there. And the result is that we have a very intuitive interface to collect data. And this is where, on the right-hand side, is the user sees through the first-person camera of the Apple Vision Pro. So you can think of it as kind of like the movie Avatar, where by wearing this, you're actually now transported to a different embodiment. You are now in the body of the humanoid robot. And that's also another advantage of using humanoid, because you have 5 fingers, the robot has 5 fingers. You don't need much training, right? Anybody come here in 10 minutes, you'll be able to collect data for us. So here are some more videos from our lab where a user is teleoperating and the motions are transmitted in real time to the humanoid. And we can also do things that are a bit more complicated, like, washing dishes, and really the limit is the humanoid hardware, whatever the hardware is capable of. So that's how we are collecting the real robot data, but you're limited by 24 hours per day. That is not enough, because we know that foundation models are extremely data hungry. We're talking about we need trillions of tokens to train any reasonable transformer these days. So how do we scale this up? How do we get more data? And the second part is what I believe to be the most interesting, which will also carry to the second principle I'm going to talk about, and that is simulation. And why are we doing it here at NVIDIA? Before NVIDIA was an AI company, we were a graphics company. GPU stands for Graphics Processing Unit. And what does a graphics company do? Game engines and simulation. And just so happens that simulation is also going to be super useful for robotics. So NVIDIA has built a set of tools, and this is called Isaac Lab. What it does is it runs physics simulation in parallel on GPUs. Basically, one GPU card can let you run simulation at 10,000 times faster than real time. And in this way, you break the physical limit of 24 hours per day. You are now just limited by compute. And just as one example, to put this number in perspective, this character learns all of these impressive martial skills by going through 10 years worth of intense training in only 2 hours of compute time on a single GPU. So it's very much like the sparring dojo, right, in the movie Matrix, where you learn Kung Fu in maybe 5 seconds of real world time, but you feel like you trained for many years. And this is the Omniverse platform. And here, this race car scene is where simulation has crossed the uncanny valley, thanks to hardware accelerated ray tracing. So in this video, not a single pixel is real. All of these are rendered in real time using ray tracing. And because we can render very complex worlds with these breathtaking levels of details, that means we can also use simulation to train computer vision models that can be much more accurate, because you can also query the ground truth states of every object's, every segmentation mask in a simulation. And we can use that to be the perception module for robots. And once we have the simulation and the real robot data, we still need all the data from the internet. And that is just the regular foundation model. Training GPT-4o, multimodal foundation models, you will collect a lot of text and videos from the internet. And the robots will still need to learn like physical common sense from lots and lots of videos online. So this line is the most amount of data. I'm talking about exabytes and probably more than that per day, but this is also the most noisy. And then for simulation, we're talking about perhaps terabytes per GPU per day. And it comes with not just the pixels, but also the actions. And that goes to principle number 2, how we think about building robotics. And I'm calling this the matrix principle. And 2 questions. First, do we live in a simulation? Right? There's this very interesting argument that all of us right now are living in the matrix, a simulation. And all the human intelligence is actually some emergent behavior that an alien civilization runs on their supercomputer, right? Their NVIDIA is now simulating all of us here, right? Well, I don't know if this is true or not, but there's one thing I know is the future of robotics will live in simulation. The robots will spend most of their lives in simulation, and that's the only way that we can collect trillions and trillions of high-quality tokens by breaking the barrier of 24 hours per day. And why does simulation work for training robots? And again, just one sentence takeaway. That's because it's easier to simulate a problem than to solve it. Let me repeat, it's easier to simulate a problem than to solve it. And here are some very compelling examples from the past literature of AI, right? This is AlphaGo. In 2016, the moment when AlphaGo beat Lee Sedol at the game of Go, and the first time ever an AI beats a human champion. The entire game of Go can be simulated in perhaps 500 lines of Python. That's the rule of Go. Extremely simple to simulate, extremely hard to solve. And another favorite example of mine is Minecraft, right? A very simple game. Minecraft is like what, a few hundred megabytes of an executable. But there are all the emergent behavior, all the interesting things that you can do. And going online and look at those Minecraft channels, just absolutely insane things. Like people built the entire Hogwarts castle, block by block in Minecraft. And someone even built a functioning CPU circuit in Minecraft because apparently the game is Turing complete. So you can build a simulation within a simulation within Minecraft. So if any of you are interested, before I started Project Groot, I had this work called Mind Dojo, and that is a framework for training generally capable agents in the game of Minecraft, where we provide a simulator as an API for AI, and we also provide lots and lots of data from the internet. So if you're interested, check it out. It's minddojo.org. But basically, simulation always fascinates me. It's easier to simulate a world than to do anything interesting in it. So given the simulation, what can we do? Right? As AI scientists, we need to ask, right? How do we generate the data? And I would say 2 ways. The self-generating data and then multiply data. And these 2 corresponds to 2 learning paradigms, reinforcement learning and imitation learning. And let's look at how to leverage simulation for these two. And we'll start from reinforcement learning. Reinforcement learning, what does it do? You give an AI a reward function. Basically, the reward function tells you what behavior is desired, what behavior isn't. And then the agent will do a lot of trial and error to maximize that reward. And a prime example is Pavlov's dog, right? Like you kind of give it some conditioning and it will respond to that reward after a while. So reinforcement learning is very good at training things that we don't even know how we do. So here's a question. How many parameters in a neural network do we need to build a cerebellum? It takes a lot of subconscious processing for us humans to exist, right? Like you sitting in the chair or maintaining balance, standing, walking, it actually takes a lot of neural processing power that you don't think about. And for humanoid robots, this problem is called whole body control. And if you're using reinforcement, it's called neural whole body control. And what are whole body control useful for? Quite a few things. Like this is test optimus walking. So navigation requires whole body control. And this is shot in our lab using Apple Vision Pro. Doing tabletop manipulation using your two hands require whole body control. And this is a latest video from Boston Dynamics, where the whole robot is manipulating objects while standing balanced at the same time. And we call this whole body local manipulation. And again, that requires whole body control. So the answer to the previous question is actually to build a cerebellum, we need 1.5 million parameters, not billion, 1.5 million parameters. So we trained this network called Hover to control the body of a humanoid robot. Basically, what this model captures is this subconscious processing that we humans do. So we have a single model that learns how to coordinate, the motors of a humanoid robot, like arms and legs, to support locomotion and manipulation. And here is roughly how this neural network works. I will send the links to the papers, so if you're interested, there are a lot more details in the papers, but today we focus on intuition. So what the neural network takes is that it's able to support different command format, like kinematic position tracking, right? Like all the position of your joints, local joint angle, right? The angle between your arms, for example, and then route tracking where there's a velocity that you need to move forward to. These are different ways that we can use to control the robot. And you can think of them as prompts. And what Hover can do is you can prompt it in arbitrary combination of these things. And that enables us to use different devices to capture these commands and to teleoperate the robot. And just as a few examples, for the VR device you just saw, right, Apple Vision Pro, this is basically head and hand pose tracking. So if you want the robot to stay balanced while standing, you use Apple Vision Pro, you track 3 points, and the rest, Hover will figure out how to make the robot stand balanced. And for RGB camera, if you have an RGB looking at you and you're using some computer vision models to recognize the pose of the human, that would be whole body pose tracking. And if you're wearing an exoskeleton, that's a more advanced way to do tracking, super precise. That would be the whole body joint tracking. And if you just, right, if you only have some joysticks, some PS5, right, game controller, then you can still control the robot, but you can only specify the root command. So Hover enables very versatile control interface to teleoperate the robot, to collect data, and also just to control it in general. So here's how we train this model. Very simple. All the ideas I talk about, all the papers today are super simple. You don't need to be a roboticist to understand it. So basically, I talk about these control modes, right? So in simulation, you pass all of these information, and then what we call privilege information, which are the information that you can query in simulators, but you cannot query in the real world. Like you can know the exact location and velocity of every joint, every atom of the robot, but you don't have that information in the real robot. So that's what we call privilege information. And given all of these, it's relatively easy to train reinforcement learning to get an oracle policy. that controls the robot. But this policy cheats because it queries things not available in the real world. So we simply mask out different control modes. We also remove these privileged proprioception, privileged information, and then we distill it into a student policy using supervised learning. And this two-stage process is very simple and very effective, because if you train this directly using reinforcement learning, RL tends to be unstable. So you want to train RL in an easy way, and then you do supervised learning on a harder problem. And this is a two-stage distillation. And once you do that, by masking out different information, then hover becomes promptable because it can take any arbitrary combination of the inputs. And here are some examples, like you can have the head tracking, or like, these whole body tracking, or simply tracking the 3 points for the robot. Or you can also do like, tracking with root velocity. So it's both tracking the pose and also moving forward like zombies. I hope, in the next version, we'll train it in a better, more natural pose. But right now, this is what we get. And you can also vary the terrains, right? It doesn't have to be flat. You can vary all the terrains and obstacles in Isaac Lab, the GPU accelerated parallel simulator. So you can run tens of thousands of humanoids in this environment. And it's also not limited to just one type of robot. Anything that can be simulated in Isaac, you can plug it into training. And then what comes out is whole body control policies where you can have the robot kind of follow certain pose and walking while maintaining balance. And in the future, we plan to deploy it to many more robots. So in this video, this is from GTC. Not every robot is running a neural network here. Some are just classical control, but hover is embodiment agnostic. All right, so that's reinforcement learning. And the second type, and the second use case of simulation is to do imitation learning. So once again, this is the Apple Vision Pro I was set up to collect human demonstration. While it's quite intuitive, it's still really slow to collect these demonstrations, right? You can see it's not that easy. It's a lot of effort. And let's say given one human demo, which is very expensive to do, like perhaps you need to take a few minutes to collect one, and over an hour, you can only collect 20 demonstrations. That's very, very little data. How do you multiply that into more data? And that's the second use of simulation. And to understand how we do this, first we need to look at what is in a robot simulation. I would say three main things, right? There are handmade objects that typically created by artists, handcrafted scenes, and hand-designed tasks. And if you do that, this is what you get, right? It's a really simple scene. If you want anything more complicated, you need artists to create those assets. But how about we ask AI models to help us automate some of these processes? Like for the handmade objects, there are text to 3D models these days that are really good. So can we ask AI to generate lots of assets for us? And we instantiate it in the simulation. And for handcrafted scenes, ultimately, it is the USD format, the Universal Scene Description Language, the USD format, which has two parts, right? The texture and some code that specify the scene layout. For the texture, let's just use Stable Diffusion. We call an AI, and it can swap out all the textures that we want in a reasonable way. No artist needed. And then, because USD is just some code, there's a tool at NVIDIA called Chat USD that's basically fine-tuning LLM to generate USD. And you can generate all different layouts for the simulation. And for the tasks, it's a bunch of code in Python. So just prompt GPT-4, Claude 3.5, whatever your favorite LLM to generate the code, and we get a diverse set of tasks specified in the simulation. Right? There's like making coffee and some kind of daily tasks around. And putting all of these together, we present RoboCasa, which is a generative simulation framework where every part of it or at least as much as possible, are generated by different AI models, from the objects to the task to all the textures and layouts of the kitchens. And in the matrix, we can have 100,000 different kitchens, right? The simulation doesn't care as long as there's enough compute that goes into it. So this is RoboCasa, generative simulation framework. And given RoboCasa, we take one human demonstration from the real world, and we can replay it and multiply it into n different demonstrations. So here are some results from the paper where we train a policy using the real world data only. And this is the important part, the takeaway. If you mix in the simulation data augmented by RoboCasa with all these variations, right, the vision model, all the variations, you will get a lot better performance out of it, just out of the box. And this is just a preliminary results, and we hope to scale this up massively. So we really take advantage of the 100,000 different kitchens that you can't afford to have in the real world. And if we apply this to humanoid, this is what it looks in Omniverse rendered, right? The humanoid is doing one motion, but it can do it in 100,000 different places. And that helps us train really, really strong perception models. So that's step one, right? RoboCasa, what it does is some kind of visual augmentation. Well, you see that the motion itself, right, it is still really hard to collect. And how do you augment not just the visuals, but also the motion trajectory? And here is a system that we built to address this problem. So on the left-hand side is what a human collected in a simulation. So basically the task is just to kind of put these two pieces together. That's it, right? This is one human demonstration. And we can edit this human demonstration by varying the position of these objects and also varying the gripper with respect to these objects. So once you replay this demonstration, it will still be successful, but it will be a machine-generated demo, right? Why do you have a human teleoperate that and demonstrate 1,000 different configurations when you can use machines to generate that, right? Let machines teach the machines. And this system we built, and a set of algorithms, is called MimicGen. And MimicGen is a very general purpose framework. So it can be applied to many different tasks. And here, they're like making coffee, insert square, 3-cube stacking. So MimicGen varies all the object configurations and generate new motion trajectories that are successful. So you get these data for free without demonstrating over and over again. And if the gripper and the robot hardware are close enough, you can also generalize even across the robots that you don't have, right? We've all been poor PhD students before, right? We only have one panda arm, what to do? You call MimicGen, and you also get data on other robot arms that you can't afford. And it also works on long horizon tasks, where it's multi-step, like preparing a coffee, you need to take some pod out of a drawer and then place it in the coffee machine and kitchen chores and sorting the bins. There are tons of variations. If you want a human just to keep teleoperating that, you need thousands of trajectories to learn any good model, but you can use MimicGen to generate the data for it. It can even do very precise tasks, like this one, which requires a bit of kind of wiggling to make sure that all the nails and these holes all line up very well. And these very precise factory tasks that you need to put a gear on it. And using MimicGen, you can generate lots and lots of data for it. Also works in the real world. We want all the data to be useful in the real world as well. And this is a figure that shows the scaling of the MimicGen generated data and the performance of the trained policy. And it's obvious that the trend is moving up, but there is also some kind of diminishing return where if you use 1,000 MimicGen generated demos and then you scale it to 5,000, it doesn't buy you too much because one, the task is relatively simple. And second, there's also some limit in the system that puts a maximal for its diversity. So this was the original MimicGen work that we applied to a single robot arm. Well, the next obvious thing is to apply it to two hands, right? And for this task, again, it is run by MimicGen. It is a bimanual task, and we call this parallel subtask because these two arms can execute the pickups in parallel, while at the end, they need to do it a bit more sequentially. So this is one type called parallel subtask. And the next is called coordination subtask, where you have the two hands that need to coordinate precisely to lift up the tray at the same time, right? To lift out the lid and put it on a box at the same time. And that requires the transformations to be applied to the hand correctly. So, everything, once you play the trajectory, it's still correct. And then there are also sequential tasks where there's a pre-task and a post-task, and the next task cannot happen until the pre-task conditions are met. So here, the humanoid robot is pouring a ball into the bowl and then place it onto the green block. And again, if you want to use Apple Vision Pro to teleoperate this, it's going to take forever to do all these variations, but you shouldn't have to do. You can also mix and match. You can do the parallel generation and then do a two-arm coordination. And we can apply this two-hand bimanual system to a set of different embodiments, like a two-gripper setting, two-hand setting. There's tray lifting, drawer cleanup, and of course, humanoid setting as well, where the humanoid is able to make coffee, sorting cans, doing the pouring, and we can generate lots and lots of data from it. And just zooming out, this is Dex MimicGen, our follow-up to the MimicGen work that focuses on dexterous manipulation. And once we have this data, we can train policies. We can also study the differences between different neural network architectures now that we have a much bigger data set. And we see that diffusion policy, a specific type, is the best across all of these. And because the tasks are much harder, we also show a much better scaling as you run the MimicGen pipeline. If you start with, let's say, 100 demonstrations that the human collected, the success rate is not great. But you can use AI, right? You can use MimicGen to generate 50 times more data, and then magically the task starts to work. And we can also transfer Dex MimicGen to real world. That's what we want to do. So we have a human teleoperate, and then we have this real-to-sim pipeline where the real trajectory is replayed in simulation. We capture it in a digital twin of the real world, and then we run Dex MimicGen to generate a huge data set, and then we apply that back to real. So this is a real-to-sim to real pipeline. You collect something in real, you replay in sim, you multiply, you do everything you want in sim, and then it transfers back to real and improves the real performance. And this is one way to use simulation in the loop. So to put it together, you have RoboCasa that takes one demonstration and multiply to n, and then you have MimicGen that gives you n times m, more trajectories. And I promise you, this is the most complex math we're going to do today. And run it in Omniverse on humanoid. This is what we see. We have really good rendering and also very high quality motion trajectories generated. I want to show that this is a clip that Elon showed on at Tesla Optimus, where there's a big farm of humans serving their robot overlords, right? By kind of teleoperating a robot, it's kind of dystopian. And the humans do the same task over and over again. Actually, for one of those like battery packing tasks, it may take thousands of demonstrations for a human to collect enough data to train a model that works. So if we can run simulation to multiply the data, we can save all of these humans from this destiny. And next, and the final principle I want to talk about is the foundation agent principle. That's also how we think about building the GR00T foundation model. So most of the research on robotics can be mapped on these three axes. The number of embodiments it can master, the number of skills it can do, and a number of realities that it can work with. And this is what I mean by embodiments. In Star Wars, there are so many different types of robots. And my question is, can we have a single neural network that can control all of them? So we don't need to develop a separate pipeline for each robot. And like 2 years ago, we had a proof of concept work called Metamorph, where we train a single neural network that can control thousands of different robots. And here, all of these robots are procedurally generated. They're quite simple. So this is a proof of concept, but you can use one set of neural network weights to control them. And here, the idea is also quite simple, right? You take each robots, and they're basically a graph of joints, and we call that kinematic tree. And you do a depth-first search, depth-first traversal through this body of the robot, and you will be able to flatten it into a sequence of tokens, where each token has some physical properties attached to it. So what does this look like? Right? It looks like a sentence written in a new grammar, where the grammar describes the morphology of the robot. And if you have lots of robots, you can convert them to lots of sentences, and each may be of different lengths, and you tokenize them. And this is just screaming transformers, right? Sequence models, screaming transformers, and that's what we do. We train the metamorph transformer that maps the sequence to the actions directly. And you have variable length sequences, but they're just like English sentences. And you apply, you map them to variable lengths of actions. And we train these robots on a few different tasks, like flat terrain, walking, complex terrains, or avoiding obstacles. And we show that using a single set of neural network weights plus reinforcement learning and accelerated simulation, we can train one neural network that rules them all. And at GTC, Jensen showed all the different humanoid robot bodies. So that's where we're going. For Metamorph 2.0, we want a single model that can control all the humanoid robot bodies, even though they are slightly different from each other. And the second axis is the number of skills that the robot agent can do. And we show that Mimigen is one way to kind of, have the robot master more skills. But can we automate some of this process? And that is the Eureka work. So we train an agent that can achieve robot dexterity at superhuman level. Well, maybe not all humans, but definitely with respect to myself, because I'm never able to do pen spinning like that. I have given up long since childhood. So now my AI can avenge my poor skills, but I am a subpar human here. And how are we doing this, right? It's actually a very complex skill to learn here. And it's not clear how to even specify the reward function for it. And what we found is basically the reward function is just a bunch of Python code, right? Like in the Isaac lab simulator, all of the robot simulation is written in these Python APIs. So what we can do is we just ask ChatGPT to do the hard work for us. Right? We give the LLM a prompt saying that please find a reward function that can make the shadow hand do pen spinning. And you pass in some context, which is basically the Isaac Lab simulator API as code. And to our surprise, GPT-4, or really any of the frontier models, is able to implement the reward function correctly for most of the time. And it's actually really surprising because these reward functions actually take trained roboticists to do. You need to be very familiar with these physics simulators to even be able to write that. But models like GPTs, they learned all the text in the world, and they probably read all the papers that I wrote before as well. So they're able to do this. And we take the generated reward function, and we pass it to 10,000 copies running in parallel on a single GPU. And we're able to quickly get results by running a reinforcement learning loop on this reward function in, let's say, 15 minutes. And that completes a loop, right? We sample reward functions, we call a massively parallel accelerated training, and then we can report the results back to GPT. And these frontier models are actually very good at self-reflection. So they can debug and they can kind of find their own problems. And sometimes they'll apologize to you and then write a better function for you. And you just repeat this loop. So it writes better and better reward functions. And here are some examples of what types of reward function edits that GPT does. And it's quite non-trivial. Sometimes it's as simple as just changing the hyperparameter, but sometimes LLM decides to change the functional form of the reward function completely. And occasionally it adds completely new components to, let's say, track the angular velocity, make some penalty on the different joint angles. It's doing something very complicated here. But all of this code is edited iteratively by an LLM. And if you do this iteration a couple of times, we see that Eureka gradually becomes superhuman with respect to expert-written reward functions. And this is a very general framework. Any skill, you can prompt Eureka to do it. In fact, for these pen spinning along different axes, you actually need different reward functions to do it. And LLM has no problem figuring this out. And for some of the tasks, like this is actually spinning pen against gravity, and it's able to write reward function to solve it. So that's Eureka. And when we were doing Eureka, it was a work purely in simulation. So the next question is, how can we transfer from the sim to the real world? And that goes to the third axis, the reality axis, where here reality means simulation plus the real world. And we see the hover work here, because for hover, we need to transfer the policy to the real humanoid. But hover is hand-tuned. But can we automate it? So we introduce Dr. Eureka. And to understand Dr. Eureka, first you need to understand DR, domain randomization. It's actually a very simple technique. In simulation, you will vary the physical parameters like gravity, friction, weights, size, and all of these parameters. Because in simulation, the physics is not going to be as realistic as the real world, right? Like no matter how good a simulation is, it will never be there completely. There will always be some imperfections in the simulation. So what you do is instead of creating the absolute most accurate simulation, you trade compute for it. You just run many, many different types of reality where the gravity is not the same, friction is not the same. And here comes the catch, right? If you have an AI model that can master 10,000 different physical parameters, then it may very well generalize to the 10,001st reality, which is the physical world that we live in. And that is the principle of sim to real, of domain randomization, a super simple idea that works super well. So again, this is the Eureka loop, right? We ask GPT to do the reward function. Well, how to do the domain randomization? Typically, what people do is you rely on your expertise, right? Domain randomization, all the parameters, you need a lot of experience, from your past papers or whatever to implement. But we're very lazy, so we just ask GPT to do it for us, right? Because domain randomization parameters are ultimately still just Python code. And to our surprise, LLMs know how to do it. They know how to do it. They can also iteratively improve it. And once you have this loop, let's transfer that to the real world. So here on the left-hand side is a simulation. On the right-hand side is the real deployment. So we train the robot dog to walk here, have Dr. Eureka write some parameters, and then it transfers zero shot without fine-tuning in the real world. And this is the Allegro hand manipulating a cube. And again, it transfers zero shot to the real hand. And finally, we decided to do something crazy, right? We want to have a robot dog to walk on a yoga ball. But the issue is the yoga ball is bouncy and it's extremely hard to simulate. In fact, very, very few simulators can do this correctly. And here, we just have a rigid ball. Like this ball isn't even bouncy. It's rigid in simulation. So the physics is completely off. And then we run Dr. Eureka, and then we just ask for it to transfer to real world, and that's what we get. Well, we have our students just walk their dog, robot dog, casually on the street on a yoga ball. So when I shared this with the public, I got a comment. So someone actually, after seeing this work, they tried it on their real dog, and their dog is not able to walk a yoga ball. I wouldn't call this superhuman, but I think this is perhaps some super dog level intelligence. And that's Dr. Eureka. So to kind of take a step back, right? Like what Eureka does is you have an LLM, and then you have it code in Isaac API to generate a reward function, right? This is one loop, and this loop involves a huge foundation model. And given this reward function, you have a second loop that does reinforcement learning to produce a small neural network that basically simulates, the dogs and the hands and all of those. So Eureka is a dual loop system. You have an outer loop that does reasoning and an inner loop that does motor control. And Dr. Eureka just takes this one step further, right? In addition to reward function writing, it also writes the sim to real configuration for it. And my question is, in the future, for Eureka++, why can't we just write more things? Why can't we just ask LLMs to do more work? Can we have it write new task, new simulation completely, or perhaps even new training algorithms that I don't know how to invent, and just have the loop running? So my dream is someday, if we implement Eureka++ correctly, all of my team will take a 1-week vacation, and then we come back and Jensen wouldn't even notice because we're still reporting updates to him. And that's the goal. And once you have all of these access and you push to the top right corner, this is where we want to be, where we have a single foundation agent that can master all kinds of different bodies and do lots of different skills, automated, and also generalize across different simulations and ultimately to the real world. This is how people train ChatGPT, right? It's a sequence model that you take text in, and then you output text, be it Python writing or poetry, summarization, reasoning, it does not matter. And ChatGPT trains this by scaling it up across lots and lots of internet text data. And I believe this is what the GR00T model would look like in terms of the form factor, where it takes as input an embodiment specification telling you what you're controlling, and an instruction in natural language, and it outputs actions. And you train GR00T by scaling this up over lots and lots of realities. And how are we doing this? We need a computing platform to do this. So this is what Jensen proposed to be the 3-computer problem for NVIDIA. The first computer is called OVX, and that's basically the graphics computer. And what it does is generate tokens, right? If you're using the transformer terminology, it generates tokens. And Robocasa, Mimigen, Eureka, all of these works in simulation I talk about falls on the first computer. And the second computer is the DGX system. And those are the H100s, A100s of the world. And they learn tokens, right? They take the generated tokens, they compress them, learn them in a transformer, and these are the foundation agent models. And finally, we deploy tokens. And that is the AGX system, the Jetson Thor series of chips that will run on board the humanoid robots. So those are the computers that deploy tokens from all of these intelligence. And then you can validate the performance of this, again, in a digital twin inside the matrix. And that completes the 3-computer problem. And there is this software orchestration framework called Osmo that we use to schedule all the heterogeneous compute workload. So if you fell asleep, don't worry. This is the one slide that you need to take home today. We talk about 3 principles: the data pyramid and the matrix that supply the data to train the foundation agent. And then we talk about the 3 computers as a computing platform that enable all of these research to happen. 3 principles, and the 3 computers. I think it's going to take a while for us to solve robotics, right? This is perhaps the last AI problem, the hardest AI problem. And on our way to solve the GR00T foundation agent, we hope that we'll build all the tools and research that will inspire the community, lift up the community, lower the barrier of entry, right, to access all of these advancements that we have built. And I believe humanoid robots will be a $1 trillion business. I don't think this is very controversial because we're talking about the entire labor market to be automated once we have these generalist robot foundation models. But using Jensen's word, right now it is a $0 trillion business because things don't work. But precisely because it is 0 trillion, it's 0 today and trillion tomorrow. So we need to start working on this right now. And I believe AGI cannot be achieved without embodiment. One day, hopefully soon, we'll build our active kitten in silicon. And embodied AI is our North Star. And I believe GR00T holds the key to this future. And please join us on our journey to the moon. Thanks.